All right, so this chapter is about applications of Newton's laws. So we've studied three laws of motion that Mr. Newton gave us, and we'll look at some of the applications of those three laws. Okay? So now, before we get into that, let me remind you of those three laws. Okay? So Newton's first law, we call it Newton's first law, even though Mr. Galileo discovered it. Okay? And what this law says is, so if zero force acts on an object, if a net force of zero acts on an object, then its velocity will be constant. So for instance, if you go to an air hockey table and get this puck moving and let go of it, the net force on this will be zero. Gravity is balanced by the normal force, and there is no friction force on this. So the net force on this will be zero, and it'll maintain a constant velocity. Okay, till it hits a sidewall or something like that. Okay, so when the net force acting on an object is zero, its velocity is constant. That is, its acceleration is zero. Okay. Newton's second law states what happens if you apply a force, if the net force is not zero. Okay? So if you have a non-zero net force, then the object will accelerate. Okay? The greater the force, the greater the acceleration. That is, its velocity will change. Okay? So you can see that Newton's first law is a special case of this. This is zero. That would imply acceleration is zero and velocity is constant. Again, that's why we call it Newton's first law rather than Galileo's law. Now, this is a vector equation. We said that if you have an equation, if you have an apple on the left-hand side, you got to have an apple on the right-hand side. Okay? And this is a scalar times a vector, which is a vector. All right, what are the units? The units for mass are kilograms. The SI units for mass are kilograms. Acceleration is meters per second square. So here's a thing that we do in physics. Rather than have to write this combination all the time, we give it a name. We sort of name a new unit, and this combination is called a Newton, in honor of Mr. Newton. Okay? And so the SI unit for force is a Newton. Okay? And here's the British and US system. That's not used much. Okay? So it's used in some specialized fields and so on. The unit for mass is a slug, and the unit for force is pounds. All right, again, this is a vector equation. For two vectors to be equal to each other, what should be true is the x component of this vector should equal the x component of this vector. The y component of this vector should equal the y component of that vector. The z component, the corresponding components are equal, and that's what we're written here. See, the x component of that vector is equal to mass times the x component of the acceleration, and so on. What these equations also tell you is if you apply a force in the x direction, you're only changing the velocity in the x direction. Okay? So if you apply a force in the x direction, you cannot change the velocity in the y or the z direction. Okay? You only get an acceleration in the x direction. Okay. Okay, Newton's third law, we're just reminding you of stuff. Newton's third law says, so if this lady is pushing on the wall pushes back on her, and that's how she propels herself. Okay? And you do this when you're walking as well. Okay? When you walk, you're pushing on the floor, and you learn static friction force prevents you from slipping, and that's what propels you forward. Okay? The floor is propelling you forward. Okay? So for instance, if the floors were very smooth and your shoes were also smooth, then you couldn't walk. Your feet would just slip. Okay. So action and reaction are equal and opposite. You will see it like, you might have seen it like that. And action and reaction forces act on different objects. Okay? So what Mr. Newton is also saying is all forces come in pairs. Okay? All right. All right, so those are the three laws of motion that Newton gave us, and we'll apply these to various situations that we encounter in life. Okay? Most of the time, it'll be this equation that we'll be applying. Okay? And if we find that an object, there are several forces acting on an object. So for instance, here's an object and there are several forces acting on this object. What are the forces acting on this object? There's this tension, here's another tension, and there's the force of gravity. Okay? So there are three forces acting on this object, and this object is at rest. So its acceleration is 0. Okay, since it's at rest. So a lot of the times we'll be applying it to static objects. So the sum of all the forces acting on this object must be 0. Okay, so that's what we'll be doing. Okay. So here's an object that is at rest. So the sum of the forces on it must be 0. Okay, so there are three forces acting on this object: gravity, this tension, and that tension. Okay, right now, till we get to chapter 9. Okay, so let me give you a counterexample here. Okay, so here's a barge. This tugboat is pushing on it, and this tugboat is pushing on it. And the barge is accelerating that way. What if this tugboat was pushing on it here? What would happen? I'm sorry?
The angle would be larger because it's pushing it up.
Okay, so if this tugboat pushed on it here, this barge would spin. Okay? Everybody understand that? So why is it not spinning now? Right. So what is happening is, so you intuitively knew this, what's happening is all these forces are going through the center of mass of the tugboat. Okay? So right now that's the situation we'll be considering. The forces acting on the tugboat are going through the center of mass. And in that case, the object won't spin. So we're keeping things simple. When we get to chapter 10, we'll have objects spinning. Okay? So right now, the way we say this is the torques of these forces are 0. Okay? In chapter 10, you'll see that the torques of the forces are non-zero, and then the object can spin. Okay? So right now, we won't consider that complication. So everything we consider now will be effectively all the forces are acting through the center of mass of the object. Okay? So what we can do is we can treat the object as a point particle. Okay? So we'll be able to draw diagrams like this, and that's a free body diagram. Okay? All right, so we've said several things here. Okay? So we're considering applications of Newton's laws, and most of the application will be of this second law formula. Okay, so we'll consider situations where several forces will be acting on an object, and if the object is at rest, acceleration is 0, that means the sum of the forces must be 0. Okay, so that's what's happening here. And there are three forces on this object, and we are interested in analyzing this situation. And what we'll do is, so like I said, effectively all the forces are acting, even though these two forces are not acting through the center of mass. What's happening is this component is canceling that, and the y components are going through the center of mass. Yeah. All right, so this object is represented by a point like that. This tension is that, and there's this tension acting on it, and third is the weight of the object. Okay? And of course, when you drive underneath this signal, what do you hope? That that thing doesn't move. Okay? So you're hoping that at all times the sum of those forces are zero. Okay? All right. Well, why would we be interested in analyzing this kind of situation? Well, so you know the weight of the object, you know the weight that you want to hang, you calculate the tension on the strings, and you make sure that the string is strong enough that it doesn't fall, it doesn't break. Okay, so that's why you're interested in analyzing stuff like this. All right, so here's a barge. We're applying this force and this force. Again, like I said, the force is going through the center of mass. And this time the barge is accelerating in that direction. Okay? So here's a free body diagram. Again, the barge is represented by a point. When can we do this? As long as the barge is not spinning, then we can do that. Okay? And effectively all the forces are going through the center of mass. Okay, so here's this force is there, this force is that one. What is this fella? I'm sorry? The resultant of these two is that one. Yep.
Is that the force the boat exerts on the tugboats?
No, that would have to be equal and opposite. This is a drag force. It's a friction force due to the water. Okay, that's what that is. So there are three forces acting on this object, and the sum of these three forces, there is the net force. Okay, and that's the direction of the acceleration of the barge. Okay, so that's what we do there. Here's a fellow riding an elevator. Okay, and there are several forces acting on this object. Okay, so if you wanted to analyze the motion of this elevator, okay, there are two forces acting on the elevator: the tension in the cable and the weight of the elevator, the weight of the entire thing. Okay, no, here's the total force on it. Okay, and then you would analyze that. But there are several components to this object. If you wanted to analyze the motion of this fella, you're only worried about the forces acting on this guy. What are the forces acting on this guy? Yeah.
His weight and the force of the elevator pushing up on him?
He's standing on a scale and the scale pushing up on him.
Oh, sorry.
There's only two forces acting on him. Okay? So there are several forces in this diagram, but if you want to analyze this fella, you only are concerned with the forces on this guy, and that's what's shown here. Okay? So the force of gravity and the force that the scale exerts on him. All right, so here's an interesting thing. So if he's not accelerating, when is he not accelerating? When will he not accelerate? Yeah, so if he's not accelerating, that means he won't accelerate when the elevator is moving at constant velocity or is at rest. Okay. So when he's not accelerating, the normal force, the force that the scale exerts, is equal to the force that gravity exerts. So when the elevator is not accelerating, the scale is reading his correct weight. What happens when the elevator is accelerating that way? When the elevator is accelerating that way, this force has to be greater than that force. So you gain weight. All right? When the elevator is accelerating this way, this force has to be greater than this force. So the scale is reading less. You lose weight. What if the elevator is accelerating this way and the acceleration is equal to g? You'd be weightless, that's right. That's free fall. Okay? And that's what happens in the International Space Station. You're in free fall. Okay? You'd be weightless. for a few seconds. All right. What's that? Yeah, till the, yeah. All right, so again, free body diagrams are, they're minimalistic diagrams. We're not interested in the structure of this in free body diagrams. A lot of times, if all the forces are going through the center of mass, we just represent the object by a point and show all the forces. Okay? So we're doing only the essential things. We're drawing only the essential things in the diagram. All right. So here's a situation that involves several objects. Okay. And then you can draw free body diagram for each object. Okay. So on this object, there are three forces acting on this object: the tension in the rope, the weight of the object, and the normal force that the table is exerting. Right now, we're not considering friction forces. If there were friction forces, the friction forces act in a direction opposite to the motion. So if this object is moving in that direction, there'll be a friction force in that direction. Okay? That's a kinetic friction force. On this object, there are two forces acting: the weight and the tension in the rope. Okay. And then you can independently analyze the motion of the objects. Okay. It so happens that the two motions are related because the magnitude of their accelerations are the same. Even though the direction of the acceleration are different, the magnitudes of the accelerations are the same. Okay, so in this diagram, we've shown that the tension in this rope, the tension on this side of the rope is equal to the tension on this side of the rope. So what are we assuming when we say that the tension is the same?
Frictionless.
What is that?
Frictionless.
What is frictionless?
It would be the pulley.
The pulley is frictionless and massless. Okay? Okay, so that's what you're assuming. So if you see, you will see situations, not in this course, but in a higher level course, you will analyze situations where the tensions are different. Then the pulley mass is non-negligible. Okay? All right, here's Atwood's machine. Mr. Atwood invented this to make falling objects accelerate at a rate smaller than g. Okay, so if this mass was not there, and if you let go of this would accelerate at g. Okay, how do you slow down this acceleration? You put a counterweight, and then the acceleration will slow down. Okay? Mr. Atwood invented this back in the day because if you drop an object, he wanted to measure the acceleration due to gravity. And if you drop an object back in the day when you didn't have fast timing device, and if your pulse was your timing device, this was too fast. Yeah. So you will see that you can make the acceleration of this guy with this machine, with the use of this machine, you can make this acceleration anything between 0 and g. Okay? So you could tune the acceleration to anything you want, okay, and then relate that to g. All right, so let me show that to you. So let's say this is the tension. Okay, as soon as I wrote this tension to be equal in the string, that means this pulley is massless and frictionless. Okay. Okay, so if you look at the motion of this guy, okay, for this guy, we'll choose this direction, downward direction as positive. So m2g minus tension is equal to m2 times a. Yeah. For this guy, again, he's accelerating. The magnitude of the acceleration is the same, and he's accelerating in that direction. For this guy, tension minus m1g equal to m1 times a. All right. Now let's add the two equations. So m2 minus m1 g equal to m1 plus m2 a. Okay. And so a is equal to m2 minus m1 . All right, now you'll see, notice this. If m1 is 0, if this is 0, what will be the acceleration of this guy? If m1 is 0, the acceleration of this guy will be g. It's a free fall. If m1 is equal to m2, if m1 is equal to m2, this is 0, and acceleration will be 0. So you can see that as you change this mass, okay, you can tune the acceleration to be anywhere from 0 to g. Okay? And that was the idea of this device. All right, now we'll talk about friction forces. Okay, so let me start off by showing you a little app. All right, so what we are seeing is this guy is pushing this box with a force of 25 newtons, but the box is not moving. Okay. Why is the box not moving? Because there's a friction force in the opposite direction. Okay. And when the box is not moving, this friction force is called a static friction force. Okay. What is the static friction force now? 20 newtons. 30 newtons. Okay. What is it now? 0. So it seems like this friction force, the static friction force, can change. Okay. And it turns out that so friction forces are denoted by little f. S tells you it's a static friction force. And the static friction force can be anywhere from 0 to a maximum value. Okay. So when you apply a force that's equal to the maximum static friction force, then the object will start moving. Okay. So that is the force you need to apply to get it moving. Okay. When it's equal to the maximum static friction force, then the object will break loose. All right, so let's see what is the maximum static friction force for this fellow. Okay. And well, I know what it is. Okay, so 115 Newton, the object is not moving. 120, no. There you go. So 124 newtons was the maximum static friction force. Okay. All right. Now what happens is once it starts moving, what will happen is there's a friction force now, but that is called a kinetic friction force. Okay. So if you apply 124 newtons, that friction force is less than the maximum static friction force. So this guy will accelerate. So, and that's what you can see this in the diagram. See the applied force, the kinetic friction force is less than that guy. And so he's accelerating. Okay. So once the object starts moving, the friction force, oops, what happened? Once the object starts moving, then the friction force becomes a kinetic friction force. And so we call it F subscript K. Okay. And if you have applied that force, the object will accelerate. Okay? So it's accelerating, so it's moving. Okay? All right. It turns out that, by the way, so if you're trying to push it this way and it's not moving, the friction force is acting in this direction. What if you try and push it this way and it's not moving? Which way is the friction force acting? In the opposite direction. Okay, so the friction force is always, the static friction force is always acting in the opposite direction of the tendency to move. Okay? And the kinetic friction force is acting in the direction opposite to the motion of the object. Okay? So friction forces always act in the direction either of the tendency to move or in the direction opposite of the motion. Okay? Friction forces act in the opposite direction of motion. Okay, we call them friction forces when it's two solid objects moving against each other. Okay, it arises because of two solid objects. If you have an object moving through air or a fluid, you have friction force as well, but that's called a drag force. Okay, so when you're moving through a fluid, it's called a drag force. And we'll talk about that in a little bit. So it's just a specialized name. Okay. That's also a friction force. Friction forces always act in the direction opposite to the direction of motion. Okay. It turns out that the friction force is independent of the velocity. It doesn't matter how fast this is moving for our case, and independent of the area of contact. Okay? So it's independent of the velocity and the area of contact. All right.
When you say it's independent of velocity,
So the friction force now is the same as now. It's independent of the relative velocity of the two surfaces. And when I say it's independent of the area, it just depends on the texture of the two surfaces. This is a smaller area of contact, but the friction force is the same. Okay? Yep.
So are you saying that the friction force doesn't increase the faster you go?
I'm sorry?
Are you saying that the friction force doesn't increase the faster that you go?
Yep. That's what I'm saying. Within limits. Mm-hmm.
But it would change the faster you accelerate.
No.
What would the applied force increase?
Yeah, well, the applied force is increased, and so that's why you accelerated. The friction force remained constant. Okay. Yep.
So the friction force kind of hits like a upper limit, and it won't exceed that limit, it just stays.
So this diagram shows you the static friction force. So what you have done is, so this is an applied force, and this is friction force. You applied this force, and the friction force was equal to that, and the object didn't move. Okay? You applied this force, the friction force was equal to that, and the object didn't move. This was the maximum static friction force, and it started moving. Okay? Once it starts moving, here's the kinetic friction force, and that's constant. Okay? And even though you're applying greater and greater force, that means it's accelerating and moving faster and faster. The static kinetic friction force is constant. Okay? So all this is within reason and approximation. Okay? So we're not talking about you going super fast and all that kind of stuff. Okay. All right, well, how does friction force arise? Okay, so here's a blown up picture of that. And, no matter how smooth the surface, It's jagged under a microscope. And the friction force arises because of these contact points. There's a bond between the atoms of this surface and that surface. So if you're trying to move in that direction, those bonds have to be broken every time you try to move. Yeah. And here's an interesting point. So when two surfaces are in contact, the actual microscopic area of contact is only of the order of 1 part in 10,000. Okay. So for this book on the table, this actual surface area of contact is about the point of this pen. Okay. So two surface areas in contact have a much smaller area of actual contact. Okay. Part of the friction force is because of the roughness of the surface. However, much of the friction is due to the attractive forces between molecules of the two objects. In fact, perfectly smooth surfaces of similar material would adhere and form a cold well. Okay, so the greater the area of contact, the greater the friction force. Yes. All right, so going back to this example, let's say if you apply a force and this object didn't move, that is called a static friction force. And you saw that the static friction force matched this force and this object didn't move. And this applied force, you can increase. So this static friction force can be anywhere from 0 to a maximum value. It can be anywhere from 0 to a maximum value. Okay, when you apply a force equal to the maximum friction force, maximum static friction force, then the object will start moving. And once the object starts moving, then this friction force is a kinetic friction force. It's called a kinetic friction force. And that is constant. Okay? That doesn't change. That's constant for the two surfaces that are in contact. All right, so the maximum static friction force is given by something called a static coefficient of friction times the normal force. Okay, friction forces, so here's the weight of the object, and there's the normal force. Right now, for this situation, the normal force is equal to the weight of the object. Okay. So the maximum static friction force is μs times the normal force. All right, let's look at this equation. This is a force. What are the units of a force? Newton. What is this? This is a force, Newton. So what are the units for this guy? It's unitless. It's dimensionless. It's just a number. Okay? And this tells you this is a measure of the stickiness of the two surfaces. Okay? What do you think its values can be? I'm sorry? Any real number. Okay? It can be 0 would imply that it's a frictionless surface, and infinity would imply that it's superglue. Okay? So this is a stickiness of the two surfaces. Okay? Once the object is moving, the friction is a kinetic coefficient, kinetic friction, and the kinetic friction is again mu k. So this is the kinetic coefficient of friction times the normal force. Okay, and this number is always smaller than this number for any two surfaces. Okay, so the maximum static friction force is always greater than the kinetic friction force. Okay. So here are some numbers. These numbers are important, so people actually measure them, and you have tables for this. Okay, so okay. So you remember this equation. Okay, so let's say you're going at that speed and you want to stop. Okay, so the greater your acceleration, the smaller your stopping distance. Okay. So anyways, so here is a rubber on dry concrete. The static friction force is 1, and the kinetic friction force is 0.8. Okay. So what these numbers tell you is, okay. Okay, nowadays you all have anti-locking braking system in your car. You guys know what those anti-locking braking systems do? What does it do?
Stops your brake calipers from seizing.
And so what does that do? Yeah, that's the anti-locking braking system. So what does it do?
It preserves the traction between your tires and the road.
What's that?
It preserves the traction between your tires and the road.
No, if you lock it, it'll traction. Okay, what anti-locking braking system does is it lets the wheel is still rolling. It is not sliding. When the wheel slides, okay, so here's your car. If the brakes lock, then the car is sliding, and what you're using is the kinetic friction force, and then you're using this number. And the acceleration is smaller, your stopping distance increases. If your wheel is rolling, you're using the static coefficient of friction, because that point is at rest, and you're using the static coefficient of friction, and then you're using this coefficient. The acceleration is greater, your stopping distance is smaller. Okay, when your wheels lock, if your car is sliding, the acceleration is 20% smaller, okay, and your stopping distance increases by about 25%. Okay, and so that's why insurance companies, if you have anti-locking braking, well, nowadays it's not an issue, but I'm old enough where in the old days they would ask, does your car have anti-locking braking system? You can go talk to your parents and they'll let you know. Yep. So, stopping distance. So look at this. Rubber on wet concrete. Why are you interested in this? When it rains. Okay. So when it rains, stopping distance increases, the mu(s) decrease by 30%, and stopping distance actually increases by about 40%. Okay. And so here stopping distance has increased by over 60%, 60-70%. Okay. So, all right, let's see what this number means. Okay, so we'll do rubber on dry concrete. Let's see what this number 1 means. Okay. So that'll give you a sense for it. Okay, so let's say we have a block of rubber. Its weight is 100 pounds. Even though it's not an SI unit, we'll do that. Okay, and so the normal force is what? It's 100 pounds. We're going to apply a force and try to get it moving. Okay, so let's say S max. So when you apply a force equal to the static friction force, so S max will get it moving, and that's equal to mu(s) times the normal force equal to mu(s) times the weight of the object. Okay. So if mu(s) is 1, to get a 100-pound object moving, you need to apply a 100-pound force. That's what that means. Okay? And when mu k is 0.8, what that means is to keep it moving at constant velocity, what you need to do is apply an 80-pound force. Okay? on wet concrete, you would need to apply a 70-pound force to get it moving and 50-pound force to keep it moving. Okay, so that's what those numbers mean. So right now the Winter Olympics are going on, and I don't understand this curling stone thing, but anyway, you've seen those guys sweeping in front of the rock. Okay. Anyway, what are they trying to do? They're trying to control this mu-K, okay, and get to their target location. All right, skiing downhill. Does anybody need a break? I'd like to finish the lecture and then we could take a break. There's 11 more slides. Anybody need a break, or we can keep going? Okay. All right, so we'll consider this fellow skiing downwards. Now we'll account for friction. Okay. So again, we'll represent this fellow by a dot, by a point. There is his weight acting downward like that, and there's an incline. But this guy is not useful, so what do we do? We break this into this component and that component, okay? So, and you guys remember, I'm sorry, this is mg sine theta. This is mg cosine theta, okay? And here is the friction force. What kind of friction is this? He's moving, so it's a kinetic friction force. And there's the normal force. The normal force is balancing that force. Okay? So those are the four forces acting on it. Okay? I mean, there are three forces acting on him, this, and that, except that we've broken this into these two components. Okay? All right, so here's a crate on a truck bed, right, when the truck is accelerating, okay, so I'm going to loosely talk about this. The truck is being accelerated by the engine, okay, but what is really happening is the engine is spinning the wheel is not slipping, and the static friction force is what's accelerating the truck. This guy doesn't have an engine. What's accelerating him? I'm sorry? Yeah, so the only thing this guy is in contact with is that. So when the truck accelerates, if he wants to slip away, but the static friction force makes him accelerate. Okay? So if you put a rocket on the truck, you might leave this guy behind if the static friction force is not up to it. Okay? Well, of course, we don't do that. But here's a situation where this can be dangerous. Okay. So the static friction force, there's a maximum value to it, and there's a maximum acceleration it can give. Okay. Generally, when you're just trying to accelerate, that's never an issue. But here's when it becomes an issue. Can you think of a situation where it could become an issue? Yeah. When you crash. So let's say this truck is going at 80 miles an hour and a wall suddenly jumps up in front of the truck. The truck stops fast. That's a large acceleration. And that static friction force is not up to it. And this is a double whammy for this guy. A wall jumps up, he gets crushed there, and then this thing is not stopped, and he gets crushed by that. And this actually happens. Okay. So every time there's a heavy load, okay, they have to chain it down both ways. Okay, so So let's say you're driving on a circular road at constant speed. Are you accelerating? Why are you accelerating? Direction is changing. Which way is the acceleration pointing? Towards the center of the circle, and so it's called a centripetal acceleration. Okay? And Mr. Newton tells us if you are accelerating, there must be a force acting on you. Okay? So where is the force coming on the car to make it go around the circle? Where's the force coming on the car?
Friction.
What kind of friction? Huh? Okay, so the car is not moving in this direction, and it is a static friction force. Okay? So the car is not moving in this direction, it's a static friction force. How does the static friction force arise? How does friction force arise? I'm sorry?
It opposes motion.
Yeah, no, but how does it arise physically? The molecules on the road are sticking to the molecules on the tire, okay? And so as you're going around the curve, you're leaving behind your tire molecules, okay? You're losing some of your tire molecules, so you're wearing out your tires. Okay? So every time you take an exit, okay, that's a curved road, you leave some rubber on the on the road. So if every exit were flat, the nation would lose billions of dollars. Okay? When static friction forces are, the nation saves billions of dollars annually on wear and tear of tires. So if they were all flat, you'd lose billions of dollars. And so how do you fix that? You bank the road. Okay, so here's what happens when you bank the road. Okay, now the normal force is greater than the weight because the normal force is perpendicular to the bank. Okay, the normal force is greater than the weight. This component of the normal force is balancing the weight, and this component of the normal force is providing the centripetal force. Okay? So now this happens only at one speed. If you go too fast, then you would have to use static friction force. If you go too slow, you would have to use static friction force in the other direction. So for instance, I don't know if you've been to this speedway here, they have a 30-degree bank, and the correct speed at that bank not to use static friction force is 90 miles an hour. It's an amazing bank. You guys should go there and check it out. All right, so let's say we have this banked road, and this component is balancing the weight, this component is providing the centripetal force. So n sine theta is this guy, n sine theta is providing the centripetal force mv squared by r. N cosine theta is that force that's balancing that. N cosine theta is mg. All right, now let's divide the two equations. So you get tan theta, the m cancels, is equal to v squared rg. Look at this. R is the radius of the circular circle you're going in. G is the acceleration due to gravity, and v is the speed at which you're going. There's something neat about this equation. Can you tell me what's neat about that equation? So we derive this equation assuming there's no static friction. You're not using any static friction. This component of the normal force provided you the centripetal force. And notice the neat thing about this is there's no mass information. Okay, if the road is banked at that angle, you don't need static friction no matter what your mass if you go at that speed. So a truck doesn't need to use static friction, a car doesn't need to use static friction. So that's the speed that is marked on all exits. Okay? So if you go at that speed, you won't need any static friction force. The road can be as icy as it wants. If you're going at that precise speed, you won't slip out of the curve. Okay? Yeah, it's very cool. All right, so like I said, that's why they go to that much trouble of banking the roads, because it does save billions of dollars. Yeah. And then it's a safety thing as well. Yeah. Of course, planes cannot make turns unless they're banked, and again, the same thing happens. Okay, so if a plane is going at a certain speed, the bank angle is related to the speed of the plane and the radius of the turn. Okay. Like that. So for a plane, it has no choice of using static friction force, so it has to. Okay. If you want to make a turn of that radius and at that speed, you have to bank at that angle. Okay. So now we'll talk about drag forces. What are drag forces? Friction forces and fluids. Okay, so it's friction force. We're just giving it a specialized name. All right, let's drop a cat. Okay. We'll drop this cat again in chapter 10. So,
Is that when he spins?
what's that?
Is that when he spins?
That's right. All right. So cats are useful for some things again. All right. So when you first drop the cat, the only force acting on it is the force of gravity. Now, as it speeds up, there's a drag force. And it turns out that this drag force is proportional to the speed square of the cat. The faster it's going, the greater the drag force gets. Okay. Now, so if you drop the cat from a high enough place, as its speed is increasing, this drag force is increasing. Well, what is the maximum it can get? Unless you shoot the cat out of a cannon, so what will happen is, as the drag force gets bigger and bigger, once the drag force is equal to the weight of the cat, now the net force on it is 0, and now it's not speeding anymore. The cat has reached terminal velocity. Okay. Yeah, so it reaches terminal velocity. Okay, so the drag force for large objects is proportional to the speed square. Okay. But for tiny objects, let's say dust in the air and stuff like that, that drag force is proportional to this velocity. Okay. So for tiny objects, they take a while to settle down, like pollen and stuff like that. Okay. But right now, let's consider big objects. So the magnitude of the resistive force when a body moves in a fluid depends on its speed in a complex way. Okay. We consider objects moving in air. For small objects falling slowly, such as dust particle falling in air, the force is proportional to speed. But for large objects, such as skydivers and stuff, the drag force is proportional to speed squared. Okay. So in this formula, the drag force is 1/2 c is the drag coefficient, okay, and that depends on the shape of the object. So for aerodynamic shaped objects, c is smaller. Okay. And this is the density of the fluid through which you're falling. And air is the area of cross-section perpendicular to your direction of motion. Okay, so if you're moving in this direction, this area is relevant. Okay, so for instance, for a skydiver falling like this area is greater than for a skydiver falling like this. So the drag for this guy is less, and his terminal velocity in this configuration is greater than in this configuration. Okay? So, for instance, half the gas you spend, okay, so this is a nuanced statement, but half the gas you spend is getting the air out of the way, the drag. So for instance, if your car gives you 25 miles an hour, 25 miles to the gallon, if you drove on the moon, you'd get 50 miles to them, all things being equal. Okay? So to get better mileage, if your car is more aerodynamic, that number is smaller, and you can get better mileage. Okay? All right, so how do we calculate terminal velocity? Terminal velocity occurs when your acceleration is 0, that is when the drag force is equal to your weight. The drag force is equal to your weight. Okay? And so you can solve for terminal velocity, and it's the square root of 2 times mg divided by the drag coefficient times, this is the density of the fluid through which you're falling, and this is the area of cross section. Okay? So if you're skydiving, if you fall in this configuration versus this configuration, okay? For this configuration, the area is smaller, your terminal velocity is greater. For this configuration, the area is greater and the terminal velocity is smaller. Okay? I think for this configuration, the terminal velocity is about 120 miles an hour. For this configuration is about 170 or 180 miles an hour. Yeah. So here are some, is this a good thing, this drag?
Depends.
Hmm?
It depends.
Depends, yep. Okay. So it's good for certain things and bad for other things. Because of this drag, you can walk in the rain. The terminal velocity of raindrops is about 20 miles an hour. That's fine, you can walk on that. Well, you can't walk around when it's hailing. Okay? So that's too fast and that'll cause damage. When it's raining golf balls, you definitely don't want to be walking outside. Okay? Or baseballs. All right, when small objects are falling through air, then the drag force is proportional to the velocity. Okay, so the quadratic dependence of air drag upon velocity does not hold if the object is very small, is going very slow, or is falling in denser than a medium. So if you drop a marble in water or oil, then the drag force is proportional to the velocity. Okay. So eta is the viscosity of the fluid. Viscosity is the friction of the fluid. So viscosity of honey is greater than viscosity of water. Okay? And so on. R is the radius of the object that is falling through it. All right, you might have heard of the term Coriolis forces. This is not really a true force. You feel that this force exists when you observe phenomenon from a rotating frame of reference. Okay, so let's see what this does. Okay, so what this diagram is saying is around a high pressure you get clockwise winds, and around a low pressure you get counterclockwise winds. Okay. So let's see how this happens. Okay, you guys know what is the radius of the Earth?
6,700 kilometers-ish.
Yeah, 6,400 kilometers, so about 4,000 miles. And so the circumference of the Earth is 2 pi times r. 2 pi is 6, hour is 4,000, so roughly 24,000 miles. And it's taking 1 hour, 1 day to complete one rotation. So the equator, at the equator, land is traveling at about 1,000 miles per hour. Yep,
So would it be traveling faster towards the poles?
you tell me. The poles, it's at rest.
Oh, no, it'd be traveling slower.
Yep,
Maybe because the radius is significantly smaller.
yep. So New York is traveling much slower. I don't know the number, but we'll make up a number. We'll take 700 miles per hour. So now you know a secret. All right. If you want to orbit the Earth, let's say the International Space Station is orbiting at 300 miles, at a height of 300 miles. It's traveling at about, to orbit, it's traveling at about 18,000 miles per hour or something like that. Okay?
The recording.
Oh. I need to get that fixed one of these days. All right. So if you want to launch a satellite and it shouldn't fall off the sky, this is for low Earth orbit, so it should be going at 18,000 miles an hour. If I'm standing at the equator, how fast am I moving? 1,000 miles an hour. So if I launch a satellite from here, I got to go from, assuming I want to go in this direction, all I have to do is speed up from 1,000 miles an hour to 18,000 miles an hour. If I give the job to Santa Claus, it's got to go from 0 to 18,000 miles an hour. So it costs you more to launch a satellite from there, okay? So that's why they want to be as close to the equator. All launch pads want to be as close to the equator as possible. So we do it from Florida. The European Space Agency launches from mobile platforms in the ocean near the equator, or you find a country on the equator where you launch from. Okay, so the savings are substantial. But Elon has blown. Yeah, anyway, okay. All right, so now let's get back to our thing. All right, so if I'm standing at the equator, I'm moving at 1,000 miles an hour. If I'm standing in New York, I'm moving at around 700 miles an hour. What is the air above the equator moving at? 1,000 miles an hour. What is the air above New York moving at? 700 miles an hour, okay? Which way does air flow? From high to low pressure, okay? So let's create a low pressure here, okay? What is the speed of this guy? It's 800 miles an hour, okay? So let's say this air now starts moving towards this low pressure. This guy was moving at 1,000 miles an hour, and the land here is only moving at 800 miles an hour. So this guy will get ahead. this air will get ahead. Okay. This air was moving at 700 miles an hour, and as he moved towards here, the land is moving faster, and so he'll fall behind. Okay. So just because you were doing this in a rotating frame of reference, you get these relative motion, you get these motions, okay? And remember, you're familiar with Newton's laws, and anytime something doesn't move in a straight line, you say there must be force acting on it, okay? And you call that a Coriolis force, okay? Okay. So around a low pressure, you get counterclockwise air motion, and around the high pressure, you'll get clockwise air motion. Okay. So that's what's happening. All right. Who taught them to fly in formation? Why are they flying in formation? You guys know bikers draft, bicyclists draft? Okay. So if you draft at the right distance and place, this guy can use as much as 50% less energy. That's what's going on here. Okay. So when they fly in formation like this, okay, this guy is using, all these guys are using less energy.
So does that mean the goose swap out that first?
There you go. All right. So if you want to go from point A to B, and if you fly all by yourself, let's say you use 1,000 joules of energy per goose. You fly in formation, each goose might use 700 joules of energy.
That's a lot.
Yep, that's a lot. Yep. So, and then, of course, this guy's working the hardest right now, but then you swap out and all that. Yeah. So these guys know physics.